Hello, everyone. Welcome back to the Graduate Online Combinators Colloquium. This week, we are very excited to have Jody McWhorter kick us off, talking about Matroid Circuit Polytopes. But before we get into it, I wanted to remind everyone, or for many of us, introduce us all to the Graduate Online Combinators Colloquium community statement. So this is a seminar by graduate students for graduate students. And way back when it was founded, our illustrious founders came up with three community principles that we hold to this day. And the first is we are all learning, which means that everyone who comes to this seminar has something to learn. Everyone is looking to find. You're not expected to know everything going into this seminar. Two, everyone has something to contribute. And so even if you see a lot of names, even if you feel like you aren't an expert in this field, or maybe what you have to offer has been offered many times before, that's not the point of the seminar. Everyone has something to contribute. Don't be afraid to ask questions. Questions are a vital part of what makes this seminar what it is. And finally, no one has all the answers. As the audience, we don't have all the answers. As the speaker will not have all the answers. And so if we keep these ideas in our heart, we are all learning, everyone has something to contribute, and no one has all the answers, we can really form the good foundation for a wonderful semester to come. But with that out of the way, I'm going to stop my share and I'm going to let Jody get her slides up. I am pleased to introduce Jody McWhorter from the University of Washington at St. Louis, speaking about oriented Matroid circuit polytopes. Jody, take it away.
All right, thank you very much. And yeah, as Mark said, I'm going to be telling you about some polytopes that I've been studying for a couple years now. And along with the lines in the community statement, I definitely don't have all the answers with these things. And in fact, I'll at the end, I might even be able to tell you a little bit of about some of the questions that I have. And if any of you guys are interested in looking at these questions, let me know. Um, and yeah, this is joint work with my advisor, Laura Escobar. And one of these days, we're going to get a preprint up on the archive. But so stay tuned for that. Um, but let me start off with some motivation for this project. So this came out of a workshop that I took place in back actually in spring of 2021 called the React Workshop. And this question was posed by Matthias Beck, who was one of the lecturers at that workshop. And he said, if you have a matroid, you have a bunch of these different constructions of polytopes that you get from those matroids. What if we take one of those constructions and apply it now to oriented matroids? So the nice thing about matroids is that with a lot of these constructions, you'll get these nice 0, 1 vectors, which are going to be the vertices of your polytopes. With oriented matroids, you add in a -1. And so how does that affect some of the things that you can get? So to start out, before I even introduce matroids, I'm going to give you an example that will carry through all of the talk. This is going to turn into the example that I can tell you the most about. And there's two different ways that you can approach this depending on your background and what makes sense to you. So the first way that you can think about my running example here is if you are familiar with root systems, what I'm doing is I'm taking the type A roots and I'm taking the positive type A roots and I'm putting them as a column of a matrix, and I'm going to build an oriented matroid out of that. If you don't know about root systems, you can also think about this as the complete graph on n nodes. So for instance, here is the n equals 3 case. So this is what my matrix looks like on the left here. And then for my graph, I've got 1, 2, and 3 nodes. And because I'm going to be building an oriented matroid, I want directed edges of my graph. And I've directed all of my edges so that they point at from the smaller number to the larger number. It turns out that directions for our polytopes aren't actually going to matter, but just to have some consistency. So this is the example that I'm going to be talking the most about. If you are wanting to follow along on your own and try some of these things on your own, here's the n=4 case. I'll be able to give you some information about this case going along, so that way if you want to, you can see what you can come up with. All right, so I've given you an example, but I haven't even told you what a matroid is, much less an oriented matroid. And there's a lot of different ways that you can define a matroid. And the thing that I'm going to be using is the circuits. And so I'm going to be using the circuit definition of an oriented matroid. So here's what circuits are for completeness. And I'm not going to go into depth into each of these conditions. I'm going to tell you the important things that I'll be using. But the gist of all of this is that we start out with a finite set. We get these circuits, which are these sets of subsets, more or less. And those subsets will have to satisfy these circuit axioms. And when you take that set and those subsets together, then we get an oriented matroid. Okay, so what exactly are these subsets that we're interested in? In the matrix case, and if we start out with the matrix, then the oriented matroid that we're building is called representable. And so really what we're looking for here is the minimal linear dependencies. So for instance, with this one here, if I take one copy of the first column and I subtract one copy of the second column, and then I add in one copy of the third column, that'll give me the zero vector. And so for the circuit that I would get from that is plus, minus, plus. And you can see also if I multiplied everything by -1, those pluses and minuses would flip, and I would get minus, plus, minus. Those are the only two circuits that I would get from this particular matrix here. Notice that I don't care about what the coefficients are. I only care about their signs. For graphs, I have something really nice where the circuits of the matroid are exactly the cycles of the. I can go counterclockwise around my graph here, and then I go, and the way that I'm ordering things is 1, 2, 1, 3, 2, 3, just to match with the columns of my matrix there. So I go plus along the 1, 2 edge, that gets a plus. I'll be going against the 1, 3 edge, that one gets a minus. And I'll be going along plus along the 2, 3 edge, so that one gets a plus. That corresponds exactly to that first circuit. And you can see that if I were to go the other way around this graph, I would get the negative of that circuit. So that kind of actually ties in to this second circuit axiom. If X is a signed circuit, then so is -X. If you want to try the n=4 case, you should get 14 circuits. So 7 unique circuits plus their negatives. All right. So this is an oriented matroid. Now, oriented matroids also have a dual and something called co-circuits, which end up being the circuits of the dual-oriented matroids. So these oriented matroids kind of come in pairs. And co-circuits, the way that you can think about these is they're the collection of signed subsets that are orthogonal to every single circuit of my original matroid. And once we have all those together, we have the dual of that oriented matroid. So what does that look like? Let's go back to our n=3 example here. And again, I've written down my circuits. I've got plus, minus, plus, and minus, plus, minus. Well, if I want something that's orthogonal to both of those, I could take, for instance, plus, plus, 0, because then the minus and the plus and the first two entries would cancel out and leave me and then have that 0 in that last column. And so then that would also give us this minus 0. Okay, so I can tell you those, but where are they actually coming from? I think the graph has a really nice way of describing where these come from, and that's through something called a minimal cut. So a minimal cut of a graph is the chopping off of certain edges that increases the number of connected components of my graph by exactly 1. So if I chop off this edge 1, 2 and the edge 1, 3, then the node 1 is its own connected component, and nodes 2 and 3 form a second connected component, and I have increased the number of connected components by 1. And the way that I kind of like to think about these new connected components is that one of them is a source set and one of them is a sink set. So this, I could think of kind of my set 1 going into my set 2, 3. And on the flip side, I could think of my set 2, 3 going into my set 1. And these would give me 2 different co-circuits. So the set 1 going into the set 2, 3, well, I'm going along both of these edges. So again, if I'm thinking of 1, 2, 1, 3, and 2, 3 as my ordering, that I've gone along the edge 1, 2, I've gone along the edge 1, 3, and the edge 2, 3 is not included at all. And I can go the opposite order or the opposite direction, and then I basically just flip those signs. All right, so these are what I'm starting out with. I'm starting with these plus minus 0 vectors. Now, what am I going to do with these? Well, I'm going to build a polytope. So if you are familiar with, or if you're not familiar with polytopes, these are general dimension generalizations of polygons. So the idea is you take your favorite set of points in d-dimensional space and you put some saran wrap around that and pull it tight. And what you're left with is some shape that has flat sides, and that's a polytope. Note that not all of the points that you start out with will end up being vertices of the polytope. Some of those could end up like in the middle of the polytope, but all of the vertices will be among that set of points that you start with. So this is a definition of a polytope. And so how are we building this polytope? What we're doing is we're taking these plus minus 0 vectors and we're turning all of the zeros, well, those are just going to stay at zeros. The pluses will become plus 1s and the minuses will become minus 1s. And once we have all of these together, then the oriented matroid circuit polytope associated to this matroid is the convex hull of all of those vectors that we get. Does anyone have any questions so far?
There was one question in the chat about good references for the definition of dual matroids or reading about oriented matroid fundamentals. I didn't want to interrupt you in the flow, but if you have.
I started out using Vic Reiner's notes on oriented matroids and found those quite helpful. I didn't really ever find a nice written out definition of co-circuit. So if anyone finds one of those, would love to know. Other than like just, oh, they're orthogonal to everything. It's like, what does that look like? But yeah, Vic Reiner's notes are, I would say, one of the more understandable resources that I found.
Excellent. And I believe Alex has a hand raised.
Yeah, I was just wondering. So I know typically like when we sort of assign sign to the various like members of a circuit of oriented matroids, right? It's defined up to interchanging the positive set and the negative set. Does that affect the definition of the polytope at all? Like, or maybe I'm misunderstanding.
Well, Well, like if you switch the positive set and the negative set, then you'll just get the negative of that circuit. Is that what you are asking about?
Um, I guess, but that's like maybe it could be a misunderstanding of mine, but that's like on a circuit by circuit basis, right? And so like how does
Oh,
that affect the
okay.
polytope as a
So
whole?
do you mean so each of these circuits is going to give us one point that I'm taking the convex hull of? Do you mean like if I were to take, for instance, like this column and make it negative?
Yeah, for example.
Yeah, okay. So that's actually a really good question. And the thing that we figured out is what's going to happen with the polytope is it's going to flip it over an axis, but it's not actually going to
Oh,
change like the shape of the polytope or anything. So it's just you're going to get something that's like isomorphic by one of the definitions of isomorphic. Like it's going to be the exact same
yeah.
shape, just flipped over an axis.
So you only have to make a choice of positive and negative, like for each circuit, and then you've obtained like everything else will be isomorphic to that polytope.
Yeah. So yeah, like with and that's kind of the same thing of with the choosing the direction of the edges in our graph. It doesn't really matter. So choose your favorite directed edge orientation of the graph, and the polytope is that you'll get is going to be the same if you have that order or if you start flipping some of the orders or
Sure. Yeah,
orientation.
it's just like with the directed graph, it's like we can sort of like right, we have sort of like a universal notion of like if it's like maybe we can like assign a convention holistically to the oriented matroid.
Mm-hmm.
Whereas like for abstract oriented matroids, there's not like a but it doesn't have an effect.
Yeah, so yeah, with it doesn't have an effect. It's just going to be flipping it over axes. Yeah, good question. That is something I wanted to uh, make sure to mention. So yeah, I've chosen this smaller numbers pointing at bigger numbers because that's a nice convention that's easy to explain. Um, but yeah, speaking of kind of general results that we've got, um, I mentioned that when you take the convex hull of points, you might not end up with every one of those points being a vertex. But actually, when you start out with the circuits, every single circuit is going to give us a vertex. So that's kind of nice, especially for counting things. We're not going to have like an upper limit for the number of vertices our polytope can have based on the number of circuits. The number of circuits and the number of vertices is going to be exactly the same, which is nice. Another thing that I can say is that in general, for at least realizable or for for at least realizable matroids, we have a lower bound on the dimension. And in the case that it looks something like this, but it's a little bit different because you don't necessarily have like edges and vertices and connected components. But in general, that is just a lower bound. But when you have a graphical oriented matroid, then for both the polytope that you get, the circuit polytope that you get, and also the circuit polytope for the dual oriented matroid, which I might sometimes call the co-circuit polytope because it's shorter, we actually do get a strict equality there. So if you give me a graphical oriented matroid, I can give you the dimension. And one of the cool things about this dimension is they're kind of these complementary dimensions. So they're both going to live in R to the number of elements, to the number of edges in the graph. And they're within that space, they're kind of living in these complementary dimensions. So if you add up the minus number of nodes and the plus the number of nodes are going to cancel out, and the plus the number of connected components and the minus number of connected components are going to cancel out as well. So that's really nice. And so most of the information that we have is about these graphical ones because they worked out much nicer than stuff in general. I see I have another hand up.
So the vectors that we have in this case, do they also show orthogonality with each other? The vector of the vertices for these two polytopes?
Yeah. And then this is like kind of a result, but kind of an example. So if we think about something that is a directed forest, well, what do we know about a forest? Well, it doesn't have any cycles. And if it doesn't have any cycles, then the only circuit is going to be the zero vector. And so then when I'm taking the convex hull of the zero vector, I get just a point. And so the circuit polytope then of a tree or a forest is going to be a single point. So then on the flip side, if I'm then asking about the dual-oriented matroid to that, so what happens then with the when you have a planar graph, actually the dual-oriented matroid actually corresponds to the graph, the dual graph of that graph that you started with. So the dual graph of a forest is a bouquet. And in that one, every edge is a circuit, or every edge is a cycle, and therefore every edge gives a circuit. And so what you end up with is this cross polytope, which is dimension equal to the number of edges in your graph. So we would expect it to be something full dimensional, and we actually get something very nice, which is this cross polytope. We can kind of extrapolate down a little bit from that. And in general, so a cross polytope is kind of like you start out with a line set, or you start out with a polytope and you just kind of keep suspending it. And so if we have a polytope, which is a oriented matroid co-circuit polytope for circuit, either a circuit or co-circuit polytope for a graphical or co-graphical oriented matroid, then we can figure out, we can suspend that polytope and still get another co-circuit polytope by either, depending on if we're looking at the circuits or co-circuits, either adding a loop to my graph or adding something called a bridge, which is another type of edges in graphs that I learned about when working on this project. So these are kind of our most general results. And there are a bunch of other things that I would like to know about these polytopes. And I'll tell you about some of those things at the end if we've got time. But for now, I'm going to focus on a specific case which comes from this type A root system or complete graph. And what we're really going to be looking at is not the circuit polytope for this type A root system or the complete graph. We're going to be looking at the co-circuit polytope. So the dual-oriented matroid for that. And in order to simplify notation, I'm just going to call it P sub n-1 rather than having to write out this script A sub star sub n-1 each time I want to talk about it. So just as a reminder, here's the graph that I'm looking at along with one of those minimal cuts shown in there. And here's the matrix that I'm starting with. And I told you about these first two co-circuits earlier. There's actually 6 of them in total. If you're following along for the n equals 4 case, there are 14 co-circuits there. And so then the polytope that I get is going to look something like this. And we also should know that this is a 2-dimensional polytope because number of edges, number of vertices here, number of, nodes of my graph. I try to use nodes when talking about graphs because we've got vertices with polytopes. That could get confusing. So number of nodes that I have here is 3. Number of connected components is 1. So my dimension is equal to 2. And in general, these polytopes are actually going to have dimension n-1, which is quite nice, nice and easy to work with. And so here's what this one will look like. It's a nice little hexagon. And what can we say about this next little hexagon? Or in general, the higher dimensional ones. Well, to tell you what I can tell you about them, I'm going to introduce one more concept here, which is Earhart theory. So here I've got my dimension, my n equals 3 case polytope here and my n equals 4 case polytope here. So if you find the 14 co-circuits. Those each of those will give you one of these vertices of this polytope here. So Ehrhart theory starts with a lattice point enumerator. So what are we doing? We're taking some positive integer t, and we're multiplying every point in our polytope by that positive integer t. So if I multiply by 1, I'm going to just get my polytope back. If I multiply by 2, I'm going to get something a little bit bigger, and this is called the second dilate of my polytope. And I can multiply by any positive integer t, and that'll give me the teeth dilate of my polytope. And then I'm interested in the number of integer points inside of that teeth dilate of my polytope. And so I can plug that into the idea with this lattice point enumerator is I can plug in the dilate of the polytope, and it's going to spit out the number of integer points inside of that dilate. So if I were to plug in t equals 1 for this polytope, I would get 7. If I were to plug in, and I can check that out here, got 1, 2, 3, 4, 5, 6, 7. So we can count. And if I were to plug that in for this polytope here, you'll have to take my word for it, you would get 15. And in general, what can we say about this? Well, Ehrhart in 1962 said that if you start out with a nice polytope, which nice here means it has each of its vertices have integral coordinates, it's convex, and it's d-dimensional. Then this lattice point enumerator turned out to be a polynomial, which is really nice, in t. So that's my dilation factor of degree d, so the dimension of the polytope. The leading term of this polynomial is going to be the volume of the polytope, or what you think of as the continuous volume of the polytope. And the constant term will be 1. So I can tell you the Ehrhart polynomials of each of these polytopes here. The one on the left, we have 3t squared plus 3t plus 1. And that should kind of make sense if I put my axes on here. We can see that the volume of this thing, well, we've got 1, 2, 2.5, 3. So the volume matches up. This one on the right side, so my n equals 4 case, this one will have polynomial 4t cubed plus 6t squared plus 4t plus 1. So again, you can see that the degree of the polynomial matches the dimension of the polytope. And, you know, I just happen to know these nice polytopes. And if you are familiar with, for instance, binomial coefficients, you might look at these and say, that looks kind of suspiciously nice. And it is actually kind of suspiciously nice. But first, I'm going to tell you about the generating function, and then we'll see a little bit more about that. So being a combinatorialist, we also sometimes like to take these things that are counting things and put them in a generating function. And for the Ehrhart polynomial, or in general, the lattice point enumerator, this is called the Ehrhart series. And it has this actually really nice form. So the denominator here is going to be 1 minus d to the d plus 1. Again, d is the dimension of the polytope. So that's always going to be this very nice consistent thing there. And then the numerator is going to be this polynomial in degree at most d. So unlike the Ehrhart polynomial, which will always have the degree matching the dimension of the polytope, this what we call H star polynomial does not necessarily have to match the dimension of the polytope. And in fact, if you start out with standard simplex, it will just be 1 for every dimension. But this is actually this H star polynomial in the numerator. Sometimes we just want to talk about the coefficients, and so sometimes we just put those in a vector and call that the H star vector. And this is a increasingly studied thing. People want to know, is it unimodal? Is it symmetric? Does it have real roots? What are the conditions of the polytope that will match up with that? So for instance, if it has palindromic coefficients, then we know that the polytope is something called reflexive. And one thing that we know about this polytope, or about this H star polynomial, is that these HI stars, all these coefficients, they will always be non-negative integers. We also know that this one will always be 1. All right, so let me tell you about the Ehrhart theory of these polytopes here. And there's a lot of names on this result. And the reason is because I'll tell you more about the reason in a few slides. But we have these polytopes. This lattice point numerator, this Ehrhart polynomial, is t plus 1 to the n minus t to the n. So it's like we have these binomial polynomials and we're subtracting off just the leading coefficient. And that should make sense because it's an n minus 1 dimensional polytope. So we don't want that highest degree term there. The Ehrhart series is also quite nice and has another recognizable polynomial in it. This numerator is the nth Eulerian polynomial. So if you are familiar with, or if you're not familiar with, if you are familiar with Eulerian polynomials, there's 2 ways that you can annotate them. So this is one of those ways. And if you aren't familiar with an Eulerian polynomial, this is a polynomial where the kth coefficient, or the coefficient of z to the k counts the number of permutations in Sn with k descents. And if you're at all familiar with Ehrhart theory, these 2 polynomials might look rather familiar because it actually turns out that the Ehrhart polynomial of just the n unit cube is this thing right here. And the Ehrhart series of the nth unit cube is this an of z over 1 minus z, now to the n plus 1. So it definitely, these polytopes definitely have some strong connection with the unit cube of that 1 dimension higher, which I think is kind of cool. And the other cool thing that is actually mainly our contribution to this whole box here is this first line that it's a graphic zonotope. And I'll tell you more about those at the end. But a zonotope is a really nice polytope. It's something that is a Minkowski sum of line segments, or can also be thought of as a projection of a cube. So the idea there is, like, let's say that these 2 pencils are my are 2 vectors, then the zonotope generated by these 2 vectors, so the Minkowski sum of these 2 line segments, essentially would be like take one of the pencils and then just kind of move it along the other pencil, and then the area that you cut out through that movement is a zonotope. So this parallelogram that you would get here is a zonotope. And I have worked with zonotopes before. I like them quite a bit. And so finding out that these polytopes were zonotopes was quite fun. And finding that they were not only zonotopes, but they're these graphic zonotopes that show up in some other papers was also pretty cool. So these polytopes here showed up as co-circuit polytopes for the, when you start out with the oriented matroid built off of the complete graph, but then we've actually found them now in 2 places. So one of them is this graphic zonotope case, and the other I'm going to tell you about through some work of Stapledon. So let me tell you about the work of Stapledon, and then I can tell you how these polytopes showed up there. So Stapledon in 2011 had this paper on what's called equivariant Ehrhart theory. So here's the formal list of ingredients, and the main takeaway from all of this is that we start out with a polytope, and we start out with a group that acts on this polytope. And so, for instance, one thing that you could have is if you have something called a centrally symmetric polytope, which means that if one vector is in your polytope, then the negative of that vector is also in your polytope. You could apply a Z2 action, which flips a vector with its negative, and then that would, for instance, that would be one example of a group action you could have on that polytope. Ours are actually centrally symmetric, but we're not going to be looking at the Z2 action. We're going to be looking at an SN action on our polytopes. So you start out with this action that fixes the polytope. And then you look at each of the kind of individual group elements and you can say, okay, if I apply this group element, then you're going to get some of the points in the polytope are going to be fixed and some of them are going to be switched around. So which points are going to be fixed and which ones are going to be switched around. And what you'll get is another polytope, which we call the fixed polytope for that group element. And then kind of when you put all of those together, you have this kind of collection of fixed polytopes of your original polytope, and then we can ask them questions about that. So for instance, the question that Stapleton posed in his paper was that if you have a lattice polytope and a group action on that polytope, then these conditions were equivalent. And he showed that condition 1 implied condition 2 and condition 2 implied condition 3. And I've put condition 1 in a different color because actually last year, there was a paper by Elias, Kim, and Supina that came out that included a counter example by Stapleton and Santos that said that conditions 2 and 3 actually don't imply condition 1. So the question about whether conditions 2 and 3 are equivalent is still open. And a lot of people are interested in figuring that out. And so I'm kind of glossing over what exactly is going on in here. I'll tell you a little bit about this equivariant H-star series in a couple slides. But this H-star something or another should sound kind of like this H-star polynomial. So essentially what we're doing is taking all of the H-star polynomials for each of the fixed polytopes and doing a little bit of other stuff with them. So in order to start out with this, or in order to address this question here, we first need to ask what are the fixed polytopes and what happens there. So here's our polytopes again. So let me tell you about the group action that we're going to be looking at on these polytopes. And the example that I have here is if sigma is equal to the transposition 2, 3. So if I look at the polytope on the left, really what I'm doing is if I'm applying this transposition 2, 3, I'm just permuting the indices of my U's. So these U's tell me something about the sets or the co-circuits. So for instance, like this U1 I had earlier, like this kind of 1 arrow to 2, 3. So this kind of in my graphical case, that corresponds to this cut where I'm kind of going along each of these edges. So the index 1 corresponds to the source set there that I had. And all I'm doing with this group action is I'm permuting these coordinates. So if I'm applying transposition 2, 3 to U3, well, 3 gets sent to U, so that gets sent up here. And for this one up here, the 2 gets sent to 3, so these two kind of switch. And then same if I look at this U1, 2 and U1, 3, those are going to switch. If I look at U2, 3, well, that if I apply that permutation to the 2, 3, well, I'm going to get 3, 2, which is the same as 2, 3. And so that one stays fixed. And also U1 will stay fixed because it has neither a 2 nor a 3. And I can do the same thing with this polytope on the right, my 3-dimensional version. I can look at each of those coordinates and ask, where are my fixed polytopes? Or where are my fixed points? And then what's the polytope that I get out of that? And so these are the polytopes that I get. So you can see like here I've got this U2, 3 and this U1, which were the fixed vertices. And it's the line segment connecting those two. On the right side, now I have a hexagon. And this is kind of nice. We started out with a hexagon in my 2-dimensional case. And so actually that does turn out to carry through. So let me tell you about this here. these fixed polytopes, all we need to do to figure out what they are is to look at the cycle decomposition. And the number of cycles in that cycle decomposition will determine the dimension of the polytope. And the polytope that you're going to end up with is really just a lower dimensional version of this polytope. So like here, I have, if I'm looking at, again, 2, 3, well, really, we can think of this as 1, 2, 3. And then here we also have 4 dimensionals, so it's 4 elements, so that's also, we get a 4. And so this is the n equals 3 case, which is a 2-dimensional hexagon. And so that's what we expect to see here. And that makes everything else really nice because we actually already computed the Earhart theory for all of these things because we did the Earhart theory for these polytopes in general. And so it's really just taking that, replacing the n's with k's, and I'm good to go. And so one of the other interesting things about these polytopes is they actually do show up in Stapledon's paper in a little bit of a confusing way and kind of not presented like this. But he had I think he had the H-star polynomial. And then it's just a direct computation from that to get the Earhart polynomial. So our real contribution here was a precise description of what the fixed polytopes are. Let's see. Yes, I told you I was going to tell you about this equivariant H-star series. So, well, we know the H-star polynomial for each of these polytopes. So how does that connect to this equivariant H-star series that Stapledon and now so many others are interested in? So it's a little bit different than the original Earhart series, but this thing on the left kind of looks like it. And in fact, if you plug in the identity element for little g is my group element. So if I plug in the identity element for that, then, well, this matrix here that I'm taking the determinant of is going to be a matrix whose diagonal is 1 minus z, and everywhere else is 0. So if I take the determinant of that matrix, I'm going to get 1 minus z to the d. So then overall in my denominator, I would have 1 minus z to the d plus 1, which is the Earhart polynomial of the original polytope. And that should make sense because the identity element had better fix the whole polytope. And so if I just plug in the identity element of my group, this should just give me back the Earhart series. And in that case, this numerator will just be the original Earhart polynomial, or sorry, the original H-star polynomial of my polytope. But if I start plugging in other group elements, kind of funky things can happen. This is called an equivariant H-star series, and that's really just talking about this numerator right here, because you're actually not necessarily going to get a polynomial. You could end up getting an infinite series up there. And so that's a part of Stapledon's conjecture. Condition 3 was that this, if you have those other conditions, then this numerator should be a polynomial. And in our case, you actually do get a polynomial, which is pretty cool. And we have a nice description for what it is. And it's kind of nice. So again, remember for each of those fixed polytopes, we had the H-star polynomial, and this K is the number of disjoint cycles in my cycle decomposition. And for each of those cycles, I'm going to get something of this form where I've got a product, or so where I've got this 1 plus z squared all the way up to z to the number of numbers in my cycle minus 1. And then I just take one of those for each of my cycles, I multiply them all together, and I get, and I multiply by this Eulerian polynomial, and that gives me this, cycles, or that permutations contribution to the H star series. The equivariant H star series. So what does that look like? Here's a nice little table for the n equals 4 case. So for n equals 4, we're looking at S4. There are 5 cycle types, or 5 permutation options with different cycle types. So this first one is the identity. And so again, this right here is my whole Ehrhart polynomial. And then my numerator here on the left, I have just the normal Eulerian polynomial. I'm multiplying just by 1 because I don't have anything else to contribute. And so then my H star, the contribution to the equivariant H star series is just that Eulerian polynomial. As I start breaking up my cycles into, or as I start breaking up my permutations into different numbers of cycles, then I can see, like here, I've got 3 cycles, which means that my polytope is the n equals 3 case, and we saw that this was the Ehrhart polynomial for that one. But now and here's my Eulerian polynomial, but now I need to multiply by this 1 plus z. And so I can kind of do that for each of these different cycle types. All right, so this is the equivariant H star series. But it turns out that this isn't the only kind of equivariant or this isn't the only group action that you can apply to these polytopes. So the other way to look at these polytopes is that they are a graphic zonotope. So remember I said that we've got the zonotope is a Minkowski sum, or a projection of a cube. The way that we're building these graphic zonotopes is you'd start out with the nodes of your graph, and all of them have to be labeled. And then you put edges between those. And now if I, for instance, have an edge between nodes 1 and 2, then the contribution to my graphic zonotope is going to be the unit standard basis vector E1, comma, standard basis vector E2, and the line segment between those two. And what turns out to be the case for our polytope is that our polytope is isomorphic to the graphic zonotope for the cycle graph. So I thought it was really interesting that we get the same polytope from 2 very different kinds of graphs. Like I'm starting out with the dual, or with the complete graph, and this one is starting out with just a cycle graph. So those are very different graphs. And this group action that we get here is from the automorphism group, which is a little bit different than what we have for our polytope. For our group action, we're starting out with the symmetric group, so just Sn. For this one, we need the automorphism group, because if I swap two nodes of my graph, then I really need the edges connected off of them to be connected to all the same other nodes. Otherwise, I'm going to get my polytope is going to change. And so what that looks like here is if I apply the permutation 2, 4, I take 2, I take 4, and they flip. So like, for instance, I couldn't apply my other previous example of 2, 3, because if I flipped 2 and 3, then I would be introducing the edges 1, 3 and the edges 2, 3, or sorry, 4, 2, which aren't in my original graph. And so then one question though is, well, for the elements of the groups that overlap, do we get the same polytope or a different polytope, fixed polytope? And the answer is that we actually get different fixed polytopes. So if I look at this permutation 2, 4 on the original group action I was telling you about, we get this hexagon in the middle. And for the graphic zonotope, you would get this quadrilateral. So not even the same number of vertices there. And it looks like I am out of time, so I will skip telling you about future directions and say thank you for listening.
Okay, hopefully we are all thanking the speaker. I realized I forgot to unmute and actually tell everyone to do that. And now, yeah, I'm opening up the floor to questions, and for some reason, I can't actually see anyone's video. So, would you like me to call, or would you like to call Jody?
You can call.
Wonderful. Alex.
So maybe this is included in the other direction slide, I don't know, but have you looked at have you and Laura perhaps looked at other graphs besides the complete graph? And sort of, I don't know, like properties that make their oriented matroid oriented matroid circuit polytopes still like zonotopes, or are there nice like digraph properties that mean nice things for the polytope?
Yeah, so we've looked at certain kinds of edges. So like for instance, a tree and a bouquet where every edge is a loop. Those were kind of the most general types of graphs that we looked at. We also we looked at mostly certain kinds of edges. We tried looking at like what happens if you start out with a graph that you know, and then what like if you delete an edge from the graph, what happens to the polytope? We didn't really see any nice, consistent way to get at that, because like some of your circuits are going to stay the same because some of the cycles will still be there, but some of them are going to change. But you'll also be introducing new circuits because something that was not necessarily a minimal cycle previously is now going to be a minimal cycle. So yeah, it'd be nice to have another nice family of graphs and to be able to say some stuff. But I would say, yeah, trees and bouquets, or in general, like edges, like nice edges, like edges that are loops or edges that are bridges or something like that.
Excellent. Trevor, would you like to ask a question?
Yeah, first, thanks so much for a great talk. I was curious, so you had this result about the dimension of the polytope.
Mhm.
And it looked to me like it was maybe like Euler characteristic like. I was curious if there's like any space that you think might. So that was the Euler characteristic of the graph itself. Is there like a general space for some oriented matroid that would give you the Euler characteristic of that space being for like a wider class more than just graphic? Does the question make sense?
Yeah,
Sorry,
I
I'm
think
mumbling a
so.
little.
I think so. I don't know. And the interesting thing is like if you don't have a graphical matroid, we like you don't necessarily even get that strict equality. So the we were looking at the type A root system because that gives you a nice graphical representation there. But if you start out with like the type BC root systems or the type D root system, actually it turns out that both the polytope and the co-circuit polytope will be full dimensional. And so like that one, those ones don't even try to like behave nicely with each other, sort of. So yeah, I don't know. I would love to be able to say more about the dimension, but yeah, the graphical case we get equality. In the non-graphical case, all we get is a lower bound, and it's definitely not necessarily strict.
Cool, thank you.
Mhm.
I did. Sorry.
No, I was going to say, Sheila, you're unmuted. Would you like to ask a question?
Oh, yes. In your table, the last table. So first of all, I have the same question that Trevor had, but yes, in that table, um, are these things ever actually polynomials?
Uh, which things?
the sum of the fixed points. Sorry, there was so much the number of fixed points in the dilation. You're taking the generating series. So it looks like, so for example, when you take a 4 cycle, this is going to simplify, right? It's just going to be 1 over 1 minus z. Is there a reason that that happens? I'm just noticing that there's a lot of cancellation.
Oh, yeah. So do you mean in this third column here?
Yeah.
Yeah. So this third column is this equivariant H star series. So you're never going to get all of the cancellation. The denominator, I think, is always going to be 1 degree higher, at least. Because in general, with the Earhart series, so this is kind of this is kind of a generalization of the Earhart series. And with the Earhart series, your numerator always has degree at most d, and the denominator will always have degree d plus 1. So you're not quite going to get that full cancellation. But yeah, so in this case, the reason that we let's see. Yeah, so the reason that we have some amount of cancellation is because we were trying kind of we were trying to get it like exactly in this form here.
I see.
Where there was this 1 minus z, and then you have this determinant that you're multiplying by. But like if I come back to this here and I just for instance, in the second case, if I look at this one right here plus 1, and this 1 minus z squared is going to be 1 minus z times 1 plus z, and my computer is hot, so it's being slow. Yeah, so if I take kind of that stuff all together, that right there will be the Earhart series of the fixed polytope itself, kind of without other stuff. And so really what we were doing at this point was saying, okay, here's my Earhart series. Now I need to multiply by 1 plus z over 1 plus z in order to get it to look like this thing here that I'm trying to model. So that's why there's a lot of cancellations, because it was intentional multiplying by various versions of 1 to make life easier.
Yeah. So going back to the Euler characteristic question, if you put t equals -1 on the left-hand side of your theorem for the sum of the fixed points, the sum, yeah, no, just what you had. Sorry, what? This one. Yes. So if you put z equals -1 there, then that's going to look like an Euler characteristic for, I believe, the fixed point polytope. Sorry, I'm not used to thinking about polytopes, so I'm thinking more topologically. Then that would look like a reduced Euler characteristic on the left.
I'm not sure what the generating series is only defined. Oh. No, I see.
I'm putting z equal to
yeah. We don't usually plug in things for z. So I don't really know what happens there.
Okay.
Yeah. That is a good question. I don't know what the different like plugging in stuff for z looks like, because yeah, it's just a generating function, and so we're interested in the coefficient of z to the something, but
Okay.
yeah, not sure.
Okay,
Thanks.
on that exciting thought, I think we're going to have to end our question period. Let's all thank Jody again. And I will end the recording.